Morning, everybody. Welcome to the middle of the week. All right. We were deep into free body diagram, or we were starting free body diagrams. We need to get deep into free body diagrams. And once we have the free body diagrams sort of introduced to you, we can start applying them. And we'll be doing quite a bit of math today after we get through the drawings. What was critical about free body diagrams in terms of like drawing the object? What should you do? Just make it simple, right? This diagram is not meant to show shape or anything like that. It's just supposed to be a simple object. Then you need, so simple object, you need to be able to have a system where you've got the forces acting on the object. And remember, there's a question you should be asking yourself when you're drawing this free body diagram, and it's what objects are pushing or pulling? If there's another object that is pushing or pulling on this thing, there's a force. And then you got to get the direction of the forces, all this sort of stuff. So, for example, if we had something that was falling through the air, well, the earth would be pulling on it, causing the force of gravity. But then there might also be air resistance, right? Acting up on it. So you need to consider all of the objects that are pushing or pulling on your main object, the thing you're drawing the free body diagram for. So here's something we didn't get to last time. Every free body diagram should have a coordinate system that tells us what direction we are calling positive. It can be sort of a standard, right? But you always want to give some indication about what direction you're calling positive X and what direction you're calling positive Y. This might seem weird, like Mr. Balogh, it's always up and it's always to the right. Well, as promised in chapter 5, we're going to start changing that. And I'll do examples of where we're going to want to change that in a bit. So, this is right here what I would consider to be a complete free body diagram. It's got forces, those forces are labeled, and there is a coordinate system. This is the foundation of the visualization process that we're going to go through for solving Newton's second law problems. You will often see in books, and you will see me do it because it's handy, you will often see another arrow attached to these diagrams, not attached, but along for the ride. It's optional, but it might be useful to you. You may want to have an arrow that indicates the direction of the acceleration. And this could be something that you know, like you know that it's speeding up in that direction, or it could be some acceleration that you are guessing or assuming. Okay? It turns out that as long as you pick wisely, right, or consistently, you can't go wrong. Even if it's opposite what's going on in reality, you'll just get minus signs. In this particular problem, I might even guess that the acceleration is pointed up. This is an object that's falling with air resistance. And so I would expect it to be moving, pretty fast and then kind of slowing down to something called a terminal velocity. What's terminal velocity? Speed at which you die. It's the fastest speed something can fall in a resisted medium. So the air friction would balance the pull of gravity. The acceleration would go to zero. Point is, it might be useful to have that acceleration arrow. And I'll give you a rule of thumb in a little bit about how you make sure that you always line up your coordinate systems with your guessed acceleration. All right. So again, that would be a complete free body diagram. What I want to do right now is I want to go through some exercises with you. Oh, let me show you this picture before we do some exercises. So this came out of a book, and they're just trying to, they're pointing out something that's really critical, okay? First of all, they're drawing their apple as just a little dot, which is fine. You can just do dot. I like squares. They give me room to maneuver on. Notice how in that middle picture there, they've made sure to put the acceleration off to the side. They're not attaching the acceleration to the free body diagram to the object. What you never ever want to do, and it's an easy mistake to make, is to attach a vector and call it MA. Now, Mr. Balogh writes the Newton's second law, backwards, I guess, right? Because usually it's force equals mass times acceleration. Do not read this as a mass times acceleration is a force. That is not what this is saying. What's a force? It's a push or a pull. And MA is neither of those things, okay? All the pushes and pulls will cause accelerations to happen. That's what this is trying to say. And the amount of acceleration will be determined by the mass. But M times A all by itself is never a force. There's never an object that causes M times A. So just be aware of that as we're going through. All right. So what I would like you to do right now in your notes is do this. Draw the free body diagram of an athlete as they are jumping off the ground, right before they leave the ground. Because as soon as they leave the ground, then what is the athlete? It's a projectile. They're in free fall, right? Okay. So I want you drawing the picture of them right before they come off the ground. And by picture, I mean free body diagram. You should be asking yourself the question, what objects are pushing or pulling on the athlete? Figure out what those objects are, go ahead and draw forces in the direction you think those objects are pushing or pulling. You've got the forces of the object, don't forget to put a coordinate system on it. And wherever you are right now, just turn to your neighbor, hold up your picture, and show them. Don't be embarrassed. Go. Talk about why you did what you did. All right, how many of you realize that maybe you missed a force or got a force wrong by showing the picture of that person? Yeah, right, okay. So how do you quickly figure out whether or not your free body diagrams are correct? But you got to do it, but how do you quickly figure it out?
You need two forces.
Okay, yeah, you need two people, right? You need somebody to be talking with, right? Now, we can leverage the internet for that, and we don't have to do it in real time. There's a class Discord out there, right? Okay, so it could be real easy to go on the Discord and, hey, here, this is what my picture, right? And then several hours later, you can go on there and see their picture. Make sure that you're not shortcutting your thought process, right? By just going on there and going, oh, well, that's what all the free body diagrams look like. I'm done. Draw them first yourself, right? And then compare them to the things that people are posting, right? So your brain needs an opportunity to do it, and then you need some sort of interaction where you can reflect it back and forth. This is why if you're trying to do it yourself, okay, it can be a real problem. I really encourage you to get together as often as you can and really be comparing what you're doing and explaining it. All right, so did you have one that was pointed down? Because what's the object that's causing that force? Gravity, right? And then how many other forces did you have? Ooh, a normal force. Why did you have a normal force? Okay, they're on the ground, right? And I told you yesterday that when two objects are in contact, there's going to be a force there. We call it the normal force because it acts perpendicular to the surface of contact. So if the floor is level, the normal force would be directed straight upwards. Okay, so where does the normal force come from? The ground, right? Where does the weight come from, the mg? The earth is the object, okay? And it can be confusing because you're like, well, Mr. Balogh, isn't the ground the earth? Well, yes, but no, right? The earth as a mass exerts a force of gravity, and we'll learn why in chapter 13. The surface of the earth, the ground, the floor, okay, is considered a separate object because of the objects coming in contact. Okay, any other forces?
Acceleration.
Acceleration is not a force. Any other forces? Well, the athlete jumping. So what objects are pushing or pulling as the athlete jumps? Well, his muscles are part of the athlete. Legs. So we're going to draw a free body diagram of the stomach and then one for the leg. No. The athlete is one box.
It's pushing towards the ground. The ground's pushing back up.
Okay, that's Newton's third law, right? And we've already taken care of the ground. Are there any other objects that are pushing or pulling on the athlete besides the earth and the ground? No. This is it. Did you see how quickly you wanted to go in and complicate things? Right? Okay? You were talking about the athlete pushing on the ground. If you want to talk about that one, we got to draw a free body diagram of the ground. We're isolating the athlete. We're asking ourselves, what things are pushing or pulling? What you're going to want to do, and I hesitate to tell you this or teach you this, but I know that your brain's going to do it anyway, so let's make sure your brain does it the right way. Students often want to think of forces first. They'll go, okay, free body diagram, start drawing arrows, right? Gravity, this, that, right? And you'll start inventing forces that don't exist. They'll be fictitious forces. Please, please, please. Make sure, if you draw an arrow on your free body diagram, that you have a real object that is causing that force that is external to the thing that you're trying to draw the free body diagram for. Right? So, my encouragement to you is to think about objects first. Like make a list of objects and then draw forces. That is a better way overall in the long run. But natural tendency is to think of forces first. Just make sure your double check is, okay, I've drawn this force. Can I name the object that's causing it? Let me give you an example. If you're at the traffic light, okay, and the light turns green and you hit the gas, what direction is the force on you? We're accelerating to the right. Everybody point in the direction of the force that's acting on you as you hit the gas and start moving forward. Everybody point. Okay, all of you are wrong. You all pointed to the left. Why did you point to the left? Because you get pushed back, right? Is it, Mr. Balogh, how can you tell me I'm wrong? I do this all the time. I did it this morning on my way here. I had to gotta move. Name the object that pushed you backwards into your seat. What direction did the car push you? Forwards. The car, that's the seat in your car, pushed you forwards. You accelerated which way? That way. Okay? Right? So the car is pushing you forwards, and yet all of you were convinced that you were being pushed backwards. Name the object that pushed you backwards.
Yourself. Does air count?
No.
The seat?
No, the seat pushed you forwards.
Friction? Oh, like that's not
Friction between you and the seat, fine. It still pushed you forwards.
our own mass with gravity.
That's your weight. What direction is that? Down. Name the object that pushed you backwards into your seat. You can't, because there isn't one. Did some invisible ogre jump on the hood of your car, reach to the windscreen and push on your chest? No! So why are you all convinced that you experienced the force backwards?
The dark side.
A misconception about how the universe works. You were accelerated forwards. You changed your motion in the forwards direction. You have inertia. What does your body not want to do? Change its motion, unless it's acted upon by an outside force. That outside force was forwards. Your reaction to that is to feel a force backwards, but you're feeling your inertia. There was no force acting on you backwards. There was just a force acting on you forwards. The air in your car is moving at the same speed as you are, so it's not exerting any significant force. How easy is it to go wrong in thinking about these things? Very, right? And again, it's not because you're dumb, it's not because you're stupid, you're amazing. It's because you have had however many years that you are alive of thinking you know what's happening when it in fact is something entirely different. And so that's part of the struggle that we have to overcome. And the free body diagram and this question of name the object is really going to help. It's going to save your bacon, right? As you get used to asking that question, making mistakes, correcting your mistakes, right? And getting used to thinking about how the universe works in its true form. All right, this free body diagram has a couple of problems. I would have, if it was me, drawn the normal force acting stronger than weight. Why? This athlete is jumping off the ground, right? They're going to accelerate off the ground. In order for there to be a net acceleration, I have to have a net force. I have to have a non-zero vector sum of these forces. And so the ones going up have to be bigger than the ones going down. I also would have considered it incomplete until you had specified a direction for positive y in this case. There's only y forces here. All right, let's do another one. Let's do this one, okay? And let's say that the car is driving to the right, just so everybody kind of standardizes on the same picture. I know kilometers per hour is roughly 60 miles an hour. It's like 57. Be thinking about all the objects that are pushing or pulling on the car. Don't forget a coordinate system. Think about the acceleration of the car. If it's moving at constant speed on a straight and level road.
Are we doing curve systems today?
All right, wherever you are in your process, show your picture to your neighbor and talk about what you did, why you did, and where you're confused. Go. All right, how many of you got this far? Got those? Got at least those two. Nope. Where's the mg? What's the object that's causing the weight? Here. Okay. Where is the normal force coming from? The ground. The car's on the road, right? Okay. What's the acceleration of this car? 0. It's traveling at constant speed in a straight line. It's not changing its direction. It's not speeding up or slowing down. So what does that mean for all the vectors that I attach to this car? What has to be true? The net force has to be 0. So if I draw a certain vector down, there better be another vector acting up that's the same length. Because I don't want to be accelerating in the vertical direction. Is the car coming off the road? Digging into the road? No, it's not doing anything. So vertically, I want the acceleration to be 0. And horizontally, I want the acceleration to be 0. How many of you drew a force pointing in the forward direction? Good. Okay. You know that that needs to be there. How do you know that that needs to be there? The car, you gotta have the gas pedal down, right? Like there needs to be something that's propelling the car forward. This is where it can get a little bit tricksy. But can you name the object that's propelling the car forward? It's the ground again. This time it's the friction between the tires and the road. You might think of it as the motor, right? But the motor is really technically part of the car, isn't it? Okay? But I wouldn't fault you for saying the forward propulsion force, right? Or something, right? You know that there's something going on there that's pushing the car forward. Because if you let off the gas, what happens? It begins to slow down. But is this a free body diagram that is balanced, showing the acceleration to be 0? Which way is this object going to accelerate? To the right. You can see, right? There's a vector pointed to the right. So in order for this car to be moving at constant speed, we need another force that's pointing to the left that is more or less the same length. But I'm not going to put a force on my free body diagram until I can name an object that's causing it. What is this force that's acting opposite the propulsion of the car? Air resistance. Mr. Balogh, I thought we were ignoring air resistance. Well, no. Right? Unless the problem says, okay? Up through chapter 4 we always did, right? But now we can start dealing with it, right? But whatever the case, so if there were no air resistance, then there would be no need for a forward propulsion force, wherever it comes from, the friction of the tires, whatever, right? Okay? But since there is air resistance, we need that constant propulsion force. Okay, it's not done because it's missing what? Coordinate system. So I would do maybe something like that. And then, you know, there's no acceleration here, so I might just write A equals 0 to remind myself, right? I'm a sloppy drawer. Sometimes my vectors aren't exactly the right lengths or whatever, and I just want to reinforce, well, they're really supposed to be. But we'll just put A equals 0 on there. All right. So, we're going to draw a free body diagram of a skier sliding downhill. I hear the snow is actually pretty good right now. I'm not a skier, but I have friends who ski, and they're very, very happy. At China Peak, I should say. One of the things that you need to know is that a hill in physics is always a triangle until we get to chapter 8. So hills are all, they don't like change their shape or anything like that. Okay. They are triangles. Okay. And so a skier on a hill, right, is going to be tilted a little bit. And technically I should be drawing this off to the side, independent of any other objects. But I find it very confusing to draw this picture if I don't have the hill in my picture. So you'll see this cheat all the time in physics textbooks. You see me do it. If something's on a hill, we often keep the hill in the picture, but we're very careful that we're only drawing forces on the object that's sliding down the hill. Okay? Exceptions to every rule, right? All right. What objects are pushing or pulling on the skier? Earth. Very good. Earth causes the skier's weight, right? What else? The normal force. So where does normal force coming from? The snow, the surface of the hill, right? The skier's in contact with the surface of the hill, so there's going to be a normal force. And now notice that normal force is perpendicular to what? The hill, right? The ground level. And here the ground isn't flat, is it? It's tilted. So we've got to make sure that that normal force tilts like that. All right, any other objects that are pushing or pulling on the skier as they slide downhill? Well, let's ignore friction for now. For chapter 5, we're going to ignore any kind of friction on the surface, air resistance. We're going to get rid of that starting now. Jonathan.
But it says he's sliding.
Yep.
Pushing against the ground forward.
Okay. A free body diagram. I'm glad Jonathan asked this question. Free body diagrams only tell you about acceleration. And is acceleration motion? No. What's motion? Velocity is motion. This diagram is going to indicate to us how the skier's motion is going to change. So, even though the skier's sliding down the hill, I'm not going to put anything on my diagram to indicate that. This is a diagram of forces and accelerations. So that brings up the topic. Which direction is the acceleration on the skier? Let's assume they're sliding down an icy hill, a snowy hill, with no resistance. What's going to happen? They're going to speed up, slow down, or keep the same speed? They're going to speed up, right? Which direction are they going to speed up? Down the hill. So I'm going to go ahead and draw my acceleration acting down the hill. We guessed that. We don't necessarily have to be right, as long as we're consistent with our choice. If we get a minus answer for our acceleration, we'll know that our direction was wrong. Okay? But now that I have assumed that the acceleration is down the slope, I have to put a coordinate system on this diagram. This is where it's going to get a little bit strange, and you're just going to have to trust me for a while here. Let me give you a rule of thumb that's going to help you. You always want to put one of your directions, x or y, in the same direction as the acceleration. One of them, not both. One of your directions, x or y axis, you want to put in the same direction as your acceleration. This is going to save you from having to do a lot of math later. Conceptually, it's a bit of a burden, but mathematically it simplifies things. So, using that rule of thumb, where we always put a positive direction, x or y, in the direction of acceleration, I'm going to make my coordinate system, my positive x, be down the slope, in the same direction as my acceleration. Now, I have to do positive y perpendicular to x. Cartesian coordinate system, right? X and y have to be perpendicular to each other. So, my two choices now remain as, do I make positive y sort of away from the slope, or do I do positive y into the slope? And the answer is it really doesn't matter. So I'm going to go ahead and put positive y to be pointing perpendicular to the surface, away from the slope. So a lot of things to digest there. When you have a hill, make sure you keep the hill in the picture if it helps you visualize what's going on. Your normal force needs to be perpendicular to the hill. your acceleration is very likely going to be in the plane of the hill, and you're going to have to tilt your coordinate system. So this right here is a complete free body diagram of that skier. That skier, in fact, is going to accelerate down the hill because there is that normal force and that weight don't cancel each other out. They're acting in slightly different directions. And if we were to add those vectors together, head to tail, we would have a net vector that points along the slope. All right, let's do a diagram of the skier sliding uphill. Maybe they've slid down and then maybe they get to a section of the run where there's a slight uphill portion. Okay? There's the skier. Are there any new objects involved when the skier is sliding uphill versus sliding downhill? No. We still have the earth causing the weight. We still have the normal force. All right? No other objects. What direction is the acceleration? Up or down the slope? It's down. What's happening to the speed of the skier as they go uphill? It's slowing down, right? So they're moving up the slope, but their speed is getting slower and slower. So that means the acceleration must be pointed down, opposite the direction of the velocity. So I know that my acceleration is down the slope, just like it was for when the skier was sliding down the hill. And I'm going to put my positive x to be down the slope and my positive y to be perpendicular to it. Please, please, please try to understand what I'm about to say. A free body diagram tells you nothing about motion. These two free body diagrams are identical. You're like, but Mr. Balogh, one of them's drawn the other way. Okay, fine, they're mirror images of each other, right? But notice, in both cases, the normal force and the weight point in the same direction. Normal force away from the slope, weight straight down. The coordinate systems are both positive down the hill and away from the hill. The accelerations are both down the hill. A free body diagram tells you nothing about motion, like what the object is actually doing. What it tells you is how the object's motion is going to change. I can tell you right now, the top diagram tells me the object's motion is going to change down the hill. The bottom diagram tells me the object's motion is going to change down the hill. And if they start at the top of the hill and they're sliding down, it means they're going to speed up. But if they start at the bottom and they're sliding up, it means they're going to slow down. And now we're back from chapter 2, right? And that confusion between acceleration and velocity. Physics 4A is a class of second chances. You constantly get to come back to these ideas. And as we do it over and over and over again, hopefully you start to realize and start to think about all the details that are there. All right, let's actually do some problems here. Some real problems, okay? So we have this problem-solving method that we use to attack all problems in physics. It really never changes. There's some details that are altered. So with kinematics, making lists, maybe drawing a little picture that's got the trajectory of the object can help, right? But when it comes to Newton's laws, especially Newton's second law, our visualization is that free body diagram. It's just too good of a tool to not use it. And then, for our strategy is actually dictated for us. We're going to apply this. There's only one equation. How bad could it be? And then, of course, we'll do math, and then we'll try to come back and check our work. So, as a model for that, okay, let's do, give me an object that you would like to see sliding down a hill. Did you say an ant?
A cat.
A cat. Wait, what do we have? Do we have an armadillo? Aardvark. We had an aardvark. Let's do an aardvark. Everybody knows what an aardvark is?
No.
It's a small animal. That's all I know. All right. So this is not a biology class. So we're going to do, and by inclined plane, I'm going to show you how to do all problems that involve hills. Right? So this is a model, right? So we'll draw the hill like this, okay? And usually what happens when they tell you there's a hill or an inclined plane or a loading ramp or whatever it is the problem says, okay? They'll give some sort of angle of incline. They'll tell you that the ramp is angled at 30 degrees above the horizontal, or that the hill has a 20-degree slope or something. They'll give you some angle. And the angle that they're talking about, unless they draw a picture for you and tell you differently, is that angle right there. So let's put our aardvark on this hill. The hill is completely frictionless. When we come back next week, we'll start adding friction to everything. And our goal, there's no problem here, but our goal is to find the acceleration of the aardvark. We're going to start with our free body diagram. And what's the question we're going to ask? What's pushing or pulling, right? What are the things that are pushing or pulling? Well, one of those things is the earth causing weight of the aardvark. Another one of those things is the hill, the surface of contact between the aardvark and the very slippery frictionless hill. Maybe it's covered in ice. Are there any other objects pushing or pulling on this aardvark? Don't really have a bunch of text to parse, but no, this is it. That's all we got. And we just finished drawing the free body diagram in this, didn't we? The skier sliding down the hill, an aardvark sliding down the hill. It's all the same physics. So what direction is this aardvark accelerating, do we think? Probably down the hill. All right, fine. Maybe I'll draw that up here. So I know I'm assuming my acceleration is down the hill, which means I'm going to make positive x be down the hill, and I'll go ahead and just put positive y perpendicular and away from the hill. Okay, so there's my free body diagram. And now for the strategized portion, I need to apply Newton's second law. Newton's second law has a bunch of vectors in it, right? And so we need to deal with these vectors now. Back when we did projectile motion, how did we deal with vectors? We had more. Is there two-dimensional motion going on here? Yes, right? It's moving both in x and y. So what do we do if we have both x and y? We break it up. And by break it up, we find components, don't we? Okay? So that means that this equation becomes an equation for everything happening in the x direction. Here I've taken the vector arrows off the top and I put x subscripts underneath it. And then everything in a similar way acting in the y direction. So, if you have three-dimensional motion, what are you going to do? We're going to put z's on it. You're going to have three equations. So already, one equation becomes two, right? Don't worry, we don't put 3D on you. We wait for 4B, physics 4B for that. Okay, right? But we'll lie a little bit. When we get to chapter 11, we'll do a little bit of 3D. So for now, just two dimensions, okay? X and Y. And we now need to go back to our free body diagram and realize that we've got a problem. One of our forces does not live in just X or just Y. One of our forces, in fact, is pointing in X and Y simultaneously. Which force is the one that's behaving? Which one is only lined up in just X or just Y? The normal force, right? The normal force is pointing in the positive Y direction. So I know that it has no components, or it just has a Y component, right? It doesn't have an X and a Y. But the weight does have x and y components. It's pointing not directly down the hill and not directly perpendicular to the surface. It's pointing off at an angle. So what I need to do is I need to find the components of the weight, mg, that lie up along the coordinate system. And so one of the things that I had to learn to do as Mr. Baloghism, or a trick, is I went ahead and I drew a coordinate system. I don't know why that one turned blue. That's weird. I drew a coordinate system kind of right on my free body diagram. At the risk of my free body diagram becoming a little bit messy, I needed something visual to anchor myself with. So those are the directions. That's my x and y coordinates, right? Because again, my x and y coordinates are tilted in this problem. And I've got to find the pieces of mg that lie just along those directions. So that means mg has to have a component that points like this, and another component that points like this. And how did I know that I had to draw that component into the hill and down the hill?
Because that's for the x and y.
No, because x, well, I got a negative y and a positive x there for components. But how did I know it had to go into the hill and down the hill?
The direction of acceleration.
No.
Direction.
The weight. What direction does the weight point? Into the hill and down the hill, right? Remember, components must always add up to what? If this is my mg vector, then I have to draw components that when added together give you what? The vector that the components are trying to tell you about, right? It doesn't actually matter if I draw them that direction or I draw them this direction. Those components are all the same. And so what you saw me draw was that one and that one. But really you're closing a triangle. Okay? And if it's easier for you to draw the complete triangle, by all means, do it down there. Just don't forget that it's down there. I tend to forget, which is why I draw it up on my coordinate system. All right. In order to find the components of any vector, we need to know an angle that vector is pointing at. We know the angle of the incline of the hill. It would be nice if we could find the angle that sits right in there. Does anybody remember what that angle is? Jonathan?
Isn't it 90 degrees?
No. Really close. No. You did this problem already.
It's just theta, right?
It's just theta. Do you remember problem number 2 on lab number 1? Where I gave you a triangle and another triangle. I said there's an angle here. Find the angle up here. And you guys found that these two angles are equal? You've done the geometry already. I don't have to do it anymore. Right? If you know the angle of incline of the hill, then you know the angle between the vector and its y component in this case. Now that we know that angle, what trig function do I use for the y component? Don't say it, just look. Why is it cosine? It's touching the angle. Right? Just look. This is going to be mg cosine theta. And the other component that is not touching the angle, we're going to give it what? Sine. How's your brain? Totally full. Over full, right?
Aren't the two angles going to be like always equal?
Yes. Your brain's probably very full. You're probably sitting there going, oh my gosh, I wish this would stop. Or Is there a nice way that I can get up and leave without anybody noticing? Right? Physics is more than drinking from the fire hose, right? It's having the entire Olympic swimming pool dumped on you at the same time. You can do this. You can get through this. It's hard the first few times. It gets easier with practice. So, don't give up. Keep pushing. Go back over these notes. Go back over the YouTube. Walk through the process. There's lots of things you've got to do, right? You got to draw a free body diagram. You got to get the coordinate system. You got to get the acceleration. I've got to find components, right? This is all the physics. Now that we've got our components, we can go ahead and write down Newton's second law. In the x direction, it's the mass times the acceleration in the x direction. And how many forces are there in the x direction? I only see one. What is it? It's mg sine theta. This one right here is the only one pointing along the x-axis. What direction is it pointing, positive or negative? Why are you saying positive? Because our coordinate system was positive down the slope, wasn't it? So I'm going to go ahead and put a positive sign on that. Notice, in writing down Newton's second law, I used my free body diagram, and I asked myself a question. What are the forces? Write them out. And then what directions do they point? Very critical to get that direction right. Okay, in the y direction, how many forces are there? I see two. Let's make a list. Normal force and mg cosine theta. Again, you're looking along the y direction, and you're just looking, right? Normal points up, mg cosine theta points into the hill. So normal force, positive or negative? Positive. Mg cosine theta, positive or negative? Negative. Make sure that you're going back through and checking those directions. All right, now we have some math to do. Our goal is to solve for the acceleration of the aardvark down the hill. I've got two equations that have acceleration in them. How do I find the acceleration? Algebra. So this is the do it step. Physics can be on pause for just a second, except for maybe one thing. We know the acceleration in the y direction. What is it? It's 0. Why is it 0? Because we made sure it was 0, right? The rule of thumb, I told you, was always put your acceleration only in one direction. In this case, it's only the x direction, isn't it? That automatically means you can set the acceleration for the y direction to be 0. If your acceleration is only in y, then you can set the x direction to be 0. It's handy. It simplifies the math. If we had not tilted the coordinate system here, we would have had to find components of acceleration, components of the normal force, right? You're ending up having to do more vector components. Here I've only had to do one vector components, right, of mg. So tilting the coordinate system saved me from having to do multiple vector coordinates. Usually saves you twice as many vector coordinates. All right. Is the y equation going to tell us anything useful about the acceleration of this aardvark? No, we know it's in the y direction 0. So really all we've got to work with is the x equation, don't we? So I have mass times, I'm going to drop the x off because I it's all in the x direction, right? mg sine theta. Solve for acceleration. What goes away? Oh, the mass can't. Okay, wait a second. Math does not dictate how the universe works. Physics does. So what happened to the mass? Why does the mass not matter? What's something you know about gravity and the acceleration gravity against all objects? It's the same, isn't it? When we did free fall, did it matter if we threw an elephant or a mouse off the edge of the building? No, it mattered to Peter, right? But in terms of physics, it made absolutely no difference. because gravity is going to accelerate all those objects the same. So it makes sense that mass doesn't matter, because gravity is the only thing that's propelling this thing down the hill. And so it doesn't matter if it's an aardvark, doesn't matter if it's an elephant, doesn't matter if it's a mouse.
So we just have to know that one equation.
Well, we've now solved just about every hill problem where there is no force in the plane of the hill, right? This is the power, right? You don't have to keep solving it over and over again, right? I now know the answer. Now, of course, I'm going to ask you to show all your work on the exam. So you want to practice this. Because what happens if the aardvark is being pushed down the hill by his buddy? Like a constant push down the hill. Does this analysis now work? No. You have to go back and redo the problem with an additional force acting down the hill. So there's flexibility in the method, but for every situation where something's just sliding up or down a hill, we're done here. But we're almost done. We've got an answer, and if we knew the angle of the hill, then we could get the answer because we know what little g is. But we need to check our answer. We need to check to see if this makes any sense. And how do you check something when you're not given any numbers? The answer is you invent something. And don't invent just random ones. Invent ones where you know what's going on. Little g is not something we can mess. I suppose we could go to Mars maybe and do this, right? But like, we're doing it on the surface of planet Earth. So really the only other thing we can mess with is the angle. Right? And I can think of two angles right now where I know exactly what the value of the sine is. No. That wasn't what I was thinking, but yes, it's square root of 2. Okay, over 2. 0 and 90. What's the value of sine at 0 degrees? 50-50 chance you guessed right. Okay, it's 0, right? And at 90 degrees, the sine is 1. So, between 0 and... What does a hill look like if it has an angle of incline of 0 degrees? It looks like a table, right? It's flat ground. And if you put an object on a flat surface, flat frictionless surface, you just put it there, is it going to accelerate anywhere? No. The acceleration will be 0, and in fact, physically, that's exactly what happens. Okay, the other extreme, 90 degrees. What does a hill with a 90-degree incline look like? It looks like a cliff. And if you slide something down a frictionless cliff, then what is it? It's in free fall, right? There's no other forces acting on it besides gravity because you don't need a normal force because there's nothing to hold up. And if we put 90 degrees into the sine there, what do we get? And a 1 times little g is? Little g, is that the acceleration for something that's in free fall? I'm now confident that this equation will tell me things at 45, 60 degrees, 30 degrees. Those are just numbers, right? Variations on a theme. In fact, as the hill gets steeper and steeper, as the value of the sine gets bigger and bigger, what's going to happen to the acceleration? It's going to get bigger and bigger, which again, makes physical sense. So that's my check. And now I can solve any problem, as long as I know the angle of the hill. And there aren't any other forces. That's the power that we're trying to help you unlock. Okay? The power that goes beyond how do I do this specific problem to, oh my gosh, I can do all of these problems. It's simply a matter of time. But every problem I approach the same way. Learn the method. Not necessarily the specifics of each problem, because it's the method that's going to give you the legs to not only walk, but you will run. And it will be amazing. All right, let's do a quiz. The good news, okay, is that I've taught you everything you need to know in chapter 5. Okay? Is this good news? There's nothing but examples hereafter, right? We've gotten through sort of that really hard conceptual part where the problem-solving method is being described to you and learning free body diagrams, and you need to come up with lists in your notes of things to check, right? I need to make sure I do this. I need to make sure I do that. And those lists are going to be different for everybody because it depends on your thought processes and how easy or hard it is to hold stuff in your brain. But let's start this example. Probably not going to have time to finish it. Let's start this example, and we'll see how far we get. On Monday, let's see, you don't have homework due this Saturday, right? Right? So you haven't even looked at the homework yet. Look at the homework. Start it. You can start doing. I know, I told you. Start doing it now, right? Okay. You have enough to basically complete all of chapter 5. I'm going to show you this a little bit, but on Monday I'll finish up chapter 5. It'll only take 15 minutes, and then I'm going to start chapter 6. And with chapter 6, we do everything we did in chapter 5. We just throw friction in. And when I say just throw friction in, I'm saying we need to spend the next 3 hours of class time figuring out what the heck's going on. It was just one more force. It's just one equation. Here we go. This is actually kind of difficult to come up with examples, but like real world, there are real world situations where this is happening. But typically, a connected object, okay, consists of two masses, M1 and M2, that are connected by a rope or a string or a chain or something. And that rope, if there's an incline involved in the problem, means one of the objects is on the incline, the other one's hanging down, or maybe the other one's on another incline. I think I gave you a homework problem where that's happening. But the point is now we've introduced a rope. And this is physics rope. Physics rope has no mass. It doesn't break. It doesn't stretch. Okay? But there's a force, a word, a name that we give to the force that ropes and strings and chains and everything else provides. What's that force called when you pull? Tension. Okay? Tension is the name of the force, right? Whenever you've got strings or ropes or chains involved. The interesting thing about tension is it can only pull. If you try to push with a tension, what happens? Nothing. Okay? So, tensions can only pull on objects. They can't push on objects, right? It's kind of the one feature and why we give it a different name than, say, normal force or anything else. Okay, so since there is physics rope attached to these objects, we know that's one of the objects that's pushing or pulling, right? If we're going to find the acceleration of the system, and now the system consists of mass 1 and mass 2. They're connected by physics string. So there's something we know about the magnitude of acceleration for both of these objects. They're connected with a string that doesn't stretch and doesn't break. It has no mass. What's the acceleration going to be? The same. If mass 2 is accelerating down at 2 meters per second squared, mass number 1 is accelerating up the slope at the same exact value. Okay? So that's an assumption we can make because we're using physics string. And if you're sitting there, well, Mr. Balogh, there's no such thing as physics string. I'll show you some next week in lab. Remind me, I'll forget. So when we start, not tomorrow, but next week's lab, say, Mr. Balogh, you promised to show us physics string, and I'll go get some. It's not a trick and it's not a joke. I have actual, real physics string. I'll explain later. All right. There's also usually a pulley, something that's changing the direction of that tension for us. That pulley is massless and frictionless. Real pulleys we'll do in chapter 10 and 11. All right. Do you get the feeling that there's like a tidal wave coming? I keep saying it, chapters 10 and 11, chapters 10 and 11, chapters 10 and 11. You'll be all right. We have lifeboats and life jackets. All right. The way you deal with connected objects is you isolate the objects, draw free body diagrams for both of them. There's going to be a free body diagram for the mass on the slope. There's going to be a free body diagram for the mass that's hanging down. And again, what question are you asking yourself as you do this? What are the objects, right? What objects are causing forces? So we know that there's a gravity that's being caused by the Earth. We know that there's a normal force being caused by the surface of contact. You've seen these several times now, so hopefully it starts to become a little bit automatic, right? I didn't know normal forces existed until my physics teacher showed me, right? So you're feeling a pattern. Okay, there is a rope, right? The physics string is attached now. So I'm going to draw that as a tension acting in the direction that the rope is pulling, which is up the slope. Are there any other objects that are pushing or pulling on mass number 1? Any other physical things in the problem? Nope. Nobody's pushing it up the hill. There's no friction. Okay, we're good. All right, that free body diagram isn't done yet. Let's transition over to mass 2 and get some forces on that one. What forces are acting on mass, or sure, what forces, we'll do it your way. What forces are acting on mass 2? Gravity, okay. So where did that one come from? The Earth, okay. Anything else? Tension, which way? Up. Those two tensions are the same, by the way, because we have a massless pulley and massless string. Any other forces? How do you know? There's no other objects, right? We took care of the string. We took care of the Earth. Is there a normal force here? Why not? No, it's not resting on anything, right? So we're good. Okay, now we need to figure out like our coordinate systems and accelerations and maybe get some vector components. So this is where you want to be careful and be consistent. When you have connected objects, pick an acceleration direction and stick with it. What do I mean by that? This system is either going to change its motion. I don't know how it's moving. Let's say it starts at rest, okay? And mass 2 wins in the sense that the weight of mass 2 is enough. That means that this system will begin to go like that, in which case the acceleration would be which way for mass 2? Down, right? Okay. But what if mass 1 was winning? Then the acceleration, I know it's easy to confuse this with motion, but it would be changing its motion in the upwards direction. So let's take a guess. And again, if our guess is wrong, we'll just get a minus sign for our answer. We'll realize the direction's off. But which one do you think wins? Mass 1 or mass 2? Mass 2, does mass 2 feel better about, and it kind of depends on the angle of the hill, and you know, if mass 1's an elephant and mass 2's a mouse, well, the elephant's going to win, right? Like, there's a lot of information I'm not giving you because I wanted to give as a generic a problem as possible. And this works for all situations, regardless of the masses and the angle. So, that's, we're going to say, we're going to guess, we're going to assume, we're going to assert that the acceleration is pointed downwards for mass number 2. That means that our direction for acceleration is now chosen for mass number 1. What's the direction of acceleration for mass number 1? Has to be up the slope. You cannot have the accelerations going in opposite directions. Why not? They're connected via a rope, and ropes can only do what? Pull. They can't push on each other, right? So, if you say that the acceleration is down for mass 2, you have to say that the acceleration is up the hill for mass 1, and vice versa, right? Pick one, and then make sure you're consistent in the direction for the other. These are separate objects, and so they can have separate free body diagrams. And yes, the acceleration is up the slope for mass number 1, and it's vertically downward for mass number 2. That's okay, but it's consistent based on how they are attached physically. What do we do for coordinate systems? What's the rule of thumb? You always do what? Make sure one of the directions is positive in the same direction as the acceleration. So for mass number 1, I'm going to call up the slope positive x. And so therefore, away from the slope, I'll call positive y. And what direction am I going to call positive y for mass number 2? down. Why am I going to call down positive for mass number 2? What's the rule of thumb? Always put the positive direction in the direction of acceleration. Why? Okay, let me show you why. For mass number 2, there's only one direction, right? The y direction? So in the y direction for mass number 2, what do I write? How do I start Newton's second law? I write m times a, and then I add up the forces. How many forces are there? 2. What are they? M2G and T, right? What direction does M2G point? What direction is that, positive or negative? It's positive, and your body and your brain went, this can't be right. It doesn't feel good. Look at your coordinate system. Down is now positive. Tension pointing up is negative. But Mr. Balogh, why not just make upwards be positive? Okay, fine. If we make upwards positive, so we have M2G, and we have tension, and we have positive y pointing upwards. And let's say you go and you write down Newton's second law. You go M2AY equals, now what would you write? It would be minus M2G plus T, right? That's wrong.
Little g has a negative in it?
Not because little g has a negative in it. Little g is just a number, 9.8. But there is a missing minus sign here. It's on the acceleration. You would have to put a minus sign on that acceleration. Because if you say up is positive, but your object is accelerating downwards, you have to check the direction of acceleration. That doesn't work for me, and over the years I've noticed, if students are going to mess up, they're going to mess up on this. I mean, you'll mess up over here too, but this is the one that's super easy to forget. So, what I teach you is, always put your positive direction of your coordinate system in the same direction as your acceleration. That lets you just write m times a equals, and the only directions you need to focus on are the force directions. You just make them consistent with your coordinate system. I found over the years that that's less cognitive load for the human brain than having to, and then remember to put that there. You do you. If you do it this way and you write it down like this, that's correct. Because this equation as written and the one on the screen are exactly the same mathematically. But if you say up is positive with the acceleration pointing down and you miss that minus sign, what am I going to do? Right? Be nice, but you will lose points. Right on the exam. Your brain needs a break, so go study philosophy or something for a little bit. Tomorrow, we do the exam autopsy. And I know there's lots of angst and anxiety about getting your scores back, but we'll get them back tomorrow. We're going to start, the first 10 minutes of tomorrow is going to be me explaining how I grade and why your life isn't over. Then you will get your exam back, and then we'll go through the test autopsy. See you then. Do your best to not miss tomorrow.